Lions. How's everybody today? Hopefully you're all doing fine. You have a great day today. We're going to be talking about something they call space. What in the world is space? They haven't been able to figure that out in 10,000 years. And you say, how come? I mean, we haven't been able to analyze and figure out and justify and rationalize space. And the answer is no. We'll find out today. Anyways, we're going to start with that, and then we're going to move on to a clown who represents the establishment. And he has made me laugh these days because of the answers he gives. They're really funny for me. I can't believe that that there are people who believe in this stuff, but the question I've got is whether he's really clowning around or he really believes in this stuff. If he really believes in this stuff, I suggest that he be institutionalized because it's really out of this world. His replies. He doesn't analyze. He doesn't seem to understand what the problem is. The fact that we don't have explanations today. And then I'm going to move on to the last segment to a fellow who gave another rain check. I keep giving him rain checks. He's asking good questions, and this time it's about ionization. So that's going to be the last part. So let's get started with space. What in the world is space? Well, let's quickly review what we did last week, which is the fact that we looked at time, and we said time is not a dimension as is portrayed by the establishment. No, it's a number line. And what is interesting, is that they say it's a dimension or a coordinate, and it turns out that time doesn't have direction, and it has orthogonality with respect to nothing. It doesn't run perpendicular to anything. It doesn't have direction, none of that. And they say it's one of these guys here. It's what our dear friend Rene Descartes invented, which is the Cartesian coordinate system. And no, time is not, doesn't belong there. Maybe in math, but not in physics. And the reason I can tell you that without any problem is that you can see those lines are running perpendicular. And, if it's perpendicular, you can talk about dimensions or coordinates because that's one of the features they have. They also would carry an arrow like you see there because they have direction. But number lines, those numbers that you see there, they have neither perpendicularity to each other, and they don't run, and they don't have direction. So something is wrong there. And so we like to distinguish that from what the establishment does. The people out there, they use these number lines, and they call them dimensions, and you can see that there is a big difference. The difference is that physics is qualitative, whereas math is quantitative. And that's what the problem is. These people confuse the tops with the bottoms there. They say that what they have down there, those numbers with an arrow and the dotted lines, they say those are dimensions or coordinates or whatever they call them. No, absolutely not. Those are not part of physics. They are known as number lines, and that's all that mathematics has. It doesn't have qualitative concepts in mathematics. Mathematics is all numbers. So these people, are bringing their math into physics and calling it either physics, straightforward, or mathematical physics, which is a synonym. And no and no. Neither one. Okay. And so, yeah, they have this thing they call time, and they say it's a dimension, but it's really a number line. Number lines, as you can see there, don't have any direction or perpendicularity, because they're numbers, they're values, they're comparisons. That's what they are. And so, what do you mean when you say 5 seconds? Well, you're making a comparison between the hand on your watch and the motion of the earth around the sun. So you're comparing two motions. That's what it is. And that doesn't have any perpendicularity or direction. So yeah, it's not a dimension or a coordinate, or a vector for that matter. No, it's a number line. Number lines don't have any direction whatsoever. You can put them in you can put numbers in any order you want. You don't have to put them sequentially. You can put them one here and the other one there. They don't have location. Okay, so you can't talk about the location of a number. And that's what these people do. And they do it also for the word field, by the way. Okay, so they have this time passes. They say constantly, time flows. It flows like by me, you know. Yeah, and they give it a direction. You know, they also put perpendicular to space. And no, it's irrational to do both. You can't put a stick to represent time, okay, and you cannot put an arrow or put it perpendicular to what? Space? What is space? And since they can't put all three dimensions there, and they always complain about that, they say, well, what we do, we represent all three space dimensions, you know, length, width, and height, we represent it with a single line. Now, that's not space. What that is called a number line. And they have a number line at the bottom and the other one, you know, standing up. That's okay if as long as they keep it within math. No problem. But this has nothing to do with physics. Physics is qualitatively only. Okay, it's explanations, rational explanations of gravity, light, magnetism, electricity, workings of the atom, that kind of thing. Right? Okay, so here we have these folks, and they created the space money diagrams. You know, time is money, so they created the space money diagrams, and they use it for both quantum and for relativity. I guess if you go upwards on the time, also known as money, coordinate or dimension or whatever that is, then you're rich. And if you go down to zero, then you're very poor. And hopefully you don't get into imaginary money. Okay, so yeah, it's all nonsense that, you know, what the mathematicians have come up with to describe, right? Which is all that they do. They cannot explain with these mathematical concepts, with these quantitative concepts. They cannot explain a mechanism. They cannot explain why, you know, my pencil falls to the floor. And they say, yes, we can. Time is warped. We warp time. And that's what they do. And, you know, what are you going to do? These are the explanations you get today. Okay, so if you go to college, the higher up you go, the more irrational it gets, because they start talking to you about, you know, warping of time, of space, you know. And the question is, you know, are these things qualitative, or are we talking about something quantitative? You know, when they talk about space, they're really talking about measurement, about, again, number lines. So even though, you know, you have length, width, and height, and that's what we normally associate with, you know, with things, that's not what they're talking about. They don't talk about things at all. They talk about measurements and about numbers that they're going to put somewhere. And so when they put the word space, it's extremely misleading, because they're not talking about space, they're not talking about dimensions, they're not talking about coordinates. What they're talking about is numbers, something they measure, and they're going to put a value there. Okay? And when they put the time, you know, they say, well, this was the location and this is the time it was at that location. That's what they're saying. Okay, so, you know, the title of the press today is, you know, Space a Frontier. You saw the Enterprise, you know, so many years going out into space and say, space, the final frontier. Where did the people in Hollywood get that? From the mathematicians, obviously, right? So is this true? You know, is space the final frontier? And so you look at the word frontier, it says that part of a country, right? Or a region, I guess, that borders another country. A boundary, a border, right? So they're talking about the boundary, like it's separating you from something else. And the question is whether space is separated from something else. That's one of the issues we got to discuss today. Okay? Can we separate space from something else? Is there something outside of space giving it shape or encapsulating or serving as a boundary? And then the other notion that they have is the colonization kind of notion, right? The land or territory that forms the furthest extent of a country, settled or inhabited regions. Okay, so you colonize a land, and up to the point where you got there, that's the frontier. What continues are the Indians. Okay, so the barbarians, in the case of the Romans, they had their limit, came up all the way to here in Germany to the Main River at times, and so yeah, that's what's called a frontier. So which is it? I mean, when we talk about space, are we saying, when we say it's a frontier, are we saying that's the part of the universe that we colonized? Maybe that would be great in in science fiction. How about as a line dividing us from whatever encapsulates space? Maybe the fifth dimension or something like that. I don't know. This is what you got to think about. Is there a limit to space where you get to a point where you hit your nose against the wall? Okay, that's the issue. Okay, and so when you have a question about space, hey, why not go to the experts? And so I went to the Stack Exchange. A bunch of so-called physicists, mathematical physicists out there. This is what they have to say about space, okay? And so the question is space a thing or is it a concept? Is it filled or is it not filled? Is it empty or full? These kinds of questions. And these are their answers. Two guys in there, and they have completely different answers, both mathematicians. Listen to them. Okay, so one fellow says, the vacuum is empty in every precise sense of the word. What we call particles in quantum field theory are states created by so-called annihilation and creation operators, which represent subtracting and adding a particle of a certain type to a state. The free vacuum is by definition precisely the state from which you cannot subtract anything. Hence, it is empty. Okay, so we cannot subtract anything from space. Okay, or the vacuum, right? And so that means that is completely empty. We call it vacuum, meaning it's empty of things, but that doesn't tell me what this vacuum thingy is. What is it? Is it a container of some kind? Here you have space is not, the other fellow, right, says space is not something seething, some seething mass of particles like electrons and positrons, or protons or antiprotons, or photons or neutrinos being created and destroyed. Space is not nothing. Okay, so one guy says it's kind of empty, like saying it's nothing. This guy's saying it's not nothing. So what is it? Well, it's got vacuum fluctuations are real. The guy just finished telling us that vacuum is empty, there's nothing there. And this guy says the vacuum is fluctuating. It's moving, it's vibrating or oscillating somehow, right? Moving up and down. So we have a discrepancy here. And these two are people who are trained at the same monastery, essentially, right? So it says they are the electromagnetic equivalent of the little ripples on the surface of the sea. Yeah, the problem with the ripples on the sea is that what's rippling is water. It's known as water, So you can talk about the rippling of water. You cannot talk about the rippling of nothing. So one guy says vacuum is empty and there's nothing there, and it's absolutely nothing. What is it that is rippling? What is it that is oscillating? What is it that is vibrating? That's the question. And so, yeah, we have a little bit of a problem there because these people are supposedly educated at these monasteries, and this is what they come up with. They still don't know. They have no idea what space is. One calls it the vacuum, says it's empty. The other guy says, no, it's full, or even if it's not full, it vibrates, the vacuum vibrates. What's vibrating? Like the ocean, the sea. No, ocean has water. That you can say it vibrates. We have waves. Yeah, we can all understand that. We cannot understand the waving of nothing. And that's where the problem is. And so the question is, again, is space a container? Here's some examples of containers. We've seen them around. Right at the bottom, you see two waste baskets, and, they are containers. One is full, so we have a container that is full. Let's empty it. Got it on the right, lower right there, right? Now it's empty, right? And so the question is, that empty one, it's an empty container, but it's a container on its own. In other words, I see something there. I see some black stuff giving it some form or background, contrast. So what I'm staring at is a thing. Can we do that with vacuum or with space or whatever they call it? We empty it. What's left? What remains behind? Do we have a waste space? Is it a container? And if it's a container, what encapsulates it to give it shape as a container? Because that's what you call a container. That's an object. That's a thing. And that's what space would be if it had something encapsulating it, giving it shape, giving it contrast. So we need that. We need to know what's on the outside of space. Okay. Turns out that you go to other experts. Here's another expert. This one's from Cora. And I think it's a she. She says, the question posed to her is, if space is expanding, what is space expanding into? Right. In other words, what is on the outside of space? What encapsulates space? That's the question. And it says, your question is based on a common misconception. Oh, so we have a common misconception. Okay, let's see what the misconception is. There wasn't ever any space for the universe to expand into. Yeah, I mean, if space is what's expanding, it would not expand into another space, right? I mean, what's the difference between these two spaces? Are we talking about two empires that, reached a border and there's one empire on one side, the other empire's on the other side? Is that what we're talking about? I mean, we got a problem because there's no space into which our space can expand into. No kidding. It does not expand into a pre-existing space at all. Yeah, there is nothing outside the universe. In other words, outside of space. Yeah, that's like saying there's nothing outside of nothing. Yeah, I agree. You cannot have nothing outside of nothing because nothing is nothing. So if nothing is what encapsulates nothing or gives contrast to nothing, there would be no contrast. We would have absolutely nothing so far. So it says the expansion of the universe is the creation of more space within the existing universe. So what they talk about is what's within. They treat it as a physical object. They're saying there's more space between the visible objects like galaxies, stars, and so on, right? But they treat it as a physical object, but they say there's nothing on the outside that would tell us that it is a physical object by definition. Because that's what an object is, that which has shape. And if you don't have anything on the outside providing the contour or the backdrop, the contrast, right? Then what are you talking about? I mean, there is no object then. And she says, this means that locations that were a certain distance apart are later slightly further apart because new space is being introduced everywhere all at once. Well, the problem there is that how is space being created? I mean, what's the mechanism? Is there a little machine that creates space? Is that what she's saying? Are we saying that, space is a commodity, a scarce resource, but we can crank the machine up and somehow, right, on the assembly line and create more space? I mean, what is this, God's garage or that we're talking about here? I mean, is this magic? It says this is the same for the Big Bang where space itself was created very rapidly. Yeah, don't tell me it was created. Tell me how it was created. Give me the mechanism. Give me the explanation, physical interpretation, right? The cause. And of course, they can't do that because it's a contradiction with this person's saying. It didn't explode into a pre-existing background. So yeah, this is the notion they have out there. They say that we have space. Space is expanding. Somehow it's growing. Something is fueling it from the inside. More space is being created. But there's nothing on the outside. So it's expanding against what? How can you visualize it? What are you going to put on the board in your presentation, right? You got a balloon, it's expanding. Okay, so it's expanding. What's on the outside? What are you going to put on the outside? You're going to nothing. Nothing is what's expanding. So you can't say it's expanding against nothing. Nothing against nothing is nothing. Okay, and here you have it. This is the famous balloon analogy, and this is what they have for the Big Bang. There's been an explosion or creation of matter and space is inside the little balloon there, okay, and inside that ball. That space, that gray stuff, that's the space. And so the question is, what's the black stuff that's on the outside? That's what I want to know. If space is on the inside and it's pushing against what? More space, you wouldn't see anything here. You would just see stars and galaxies and whatever, right? Matter. And so here we stop it, and there you see, what is this black stuff? Okay, that's what we want to know. And they're saying, all these people are saying the same thing. The official version is that there is no background. There's nothing against which space expands, and space is the black stuff, or it ain't. So what is the black stuff if it's not space? You can't say it's space because space is what's expanding, and so we gotta, we're chasing our tails around. That's what we're doing here. Okay, so that's where the problem is. And if you don't know what space is, I don't know what kind of physics you can teach or you can even learn, right? If you haven't identified in 10,000 years what space is, or defined it, or justified it, or rationalized it. If you haven't done that, what kind of physics are you going to do? Because space is half the universe. It's half matter, half space, right? It's either things that exist out there and that which doesn't, which is space. Space doesn't exist because it's not a physical object, and exist requires a physical object that has location. You don't like the definitions? No problem. Challenge them, come up with your own definition. But, don't tell me that you don't like the definition. That's a poor defense, okay? Okay, so here's my version of what space is. Very to the point, down to the point. Okay, there it is. Something is an object, right? Or a thing, entity, all those words are synonyms. Body, structure, physical, all those mean the same thing in physics, right? That which has shape. That's what a physical thing is. That which has shape. All objects have shape. What is nothing? In other words, space, vacuum, nothingness, void, whatever you want to call it, right? Zip. That which doesn't have shape. So we have that which has shape is the antonym of that which doesn't have shape. Now we can use those two words consistently. The universe is, the word universe, right, is made of those two things. In other words, it's got objects, the things, the atoms, the stars, the galaxies, light, gravity, whatever mediators serve for those purposes. That's on the one hand, we'll call all of that matter, right? A lot of mathematicians don't like that. They say, no, it's energy, that's not matter. No, it's all matter because we're talking about objects, and all objects are matter. Matter is simply objects that exist. That's what it is. And so that's the definition of the word matter. Again, you don't like the definitions? Hey, come up with a better mousetrap. And the other side is space. The emptiness, the nothingness that's out there. What is that? And it's not a what. Okay? It's that which doesn't have shape. All whats have shape. There's not a single what, a single object, a single thing in the universe that doesn't have shape. Because that's the definition of a thing. But if you know of a thing that doesn't have shape, well, I'd like to hear about it, okay? And we're not talking about the thing of ordinary speech. We're talking about the thing for the purposes of physics, about an object, okay? That's what we're talking about. It's either an object or it's a concept, okay? You can't get away from that. And you can see how beautiful that dark space is. Absolutely beautiful, stunning. And I had to put a border to it simply because I have to show something. I'm saying that nothingness, that void, that, blackness, that's space. And it's not a what, it's not a thing. It's the absence of things, meaning it doesn't have shape. Okay? It's not a container. And I'll tell you why it's also not a container in a way, because you cannot escape it on the one hand. In that sense, you could say, well, maybe it is a container. But on the other, you do not displace it. When you occupy space, an astronaut, a spaceship goes out into space, It's not like a fish that displaces water in the ocean. It's either the fish or the water, right? That's not the case here. The good thing about space is you can occupy space without pushing some space over. It's not a physical object. And certainly we do not have this nonsense where that space is made of particles called virtual particles that pop in from the void, from space, come into existence and go back out of existence to form space. What is that? That's absolute poppycock. And again, all that's got to do with equations and absolutely nothing to do with physics, okay? And so, the other issue that you got to consider is whether, if space is a physical object, they talk about it being infinite. Oh, infinite space. And a lot of people have asked that question over the years of the centuries, really. Does space have a border? Does space, which is what the presentation is about. Is there a limit to space? Can you go there forever and finally at some point encounter a wall? Or is it infinite, as they say? Well, the word infinite is poorly used. It's misused in that context. There is no such thing as infinite. Infinite is an irrational term. Why is it irrational? Because it's an adjective. Adjectives in physics can only be used to qualify things, objects, entities, right? Bodies. You can qualify them with, say it's black, it's white, it's big, it's small, that kind of thing, right? But you cannot say it's infinite because the definition of thing is that which is finite. So finite and thing are synonyms, and what you're saying is it's an infinite finite. That's essentially what you're saying. And so that's what is it? An oxymoron, right? It's self-contradiction. So you can't use the word infinite anywhere in science. It's an irrational term. What people are talking about when they talk about infinite or infinity, they're really talking about incessant or incessantly, moving incessantly. You're qualifying motion. Whether you use incessant or incessantly, incessant is not an adjective for the purposes of physics. You're talking about motion. You're qualifying motion. You're modifying motion. And so, this is what they're really talking about here. I illustrated it a little bit. When you walk around the earth, you can say the earth is finite. But not like good old Stephen Hawking said, it's unbounded also. Well, unbounded in the sense you don't encounter a fence when you go around. Yeah, there's no fence. But he's not referring to that. They're using the word unbounded wrong here. They put the word unbounded when they are referring to incessant motion. They're saying you can walk around it forever because you won't encounter a fence. That's got to do with incessant walking, not with it being unbounded the way he's intending it. And so, again, when you look at space, you got to be very careful with your language. You can't use the word infinite for space. Okay? And besides the fact that, the word infinite has come from mathematics. What are they saying? What is the context of the word infinite? They're saying you can count infinitely forever, right? And you will not find the last number. So they put the infinity, lying down 8. Figure 8 there, and they say, oh, it's infinite. But what are they referring to? They're saying that you can count incessantly and not find a final number. Yeah, you can add a number 1 to infinity. Just add a number 1, and now you got infinity plus 1. And you can go on forever, meaning you can count forever. You can count incessantly, not that it's unbounded or finite, right? So again, you got to be very careful. Words like bounded or unbounded, finite, those adjectives can only be used to qualify things. You cannot use them to qualify concepts such as space, which is nothingness, which is not a thing, right? You cannot say space is unbounded. You can only say that if space is an object, and if it's an object, hopefully it is bounded. It can't be unbounded. Okay, so all these things you got to keep in mind when you come up with your notion of space. Okay, let's move on to another fellow here, our Clown. He's a clown. He makes me he makes me laugh. Some of the answers he gives, and I love it. Absolutely love all that he's got to say. So here's the first thing he criticized. Criticizing the rope model, okay? And by the way, we encourage people to criticize the rope model, hopefully from a rational point of view and not like this fellow who comes up with all kinds of nonsense. But, we do want criticism, and I'm going to have an example at the end of this fellow who asked a question about ionization, and I'm going to answer him today. But let's go with this fellow first, and here it goes. He says the following. He says, Bill's ropes are invisible and untouchable, or intangible, right? It's inconsistent with observation and experiments. Absolutely. Yeah, it's totally inconsistent with observation and experiments. You can't go out there. Here I have a little fellow. Okay, and he goes out there. He's a particle mathematician. He's going to go to the lab right there over there at CERN in Switzerland. He's going to observe particles. He's going to observe energy. He's going to observe fields. Yeah, you can't observe concepts, So in this sense, they're all blind. They can't see the stuff they're working with, but they insist on going to the lab and running an experiment. Why are they running an experiment? What's that going to tell them? I mean, if it gives them a clue, that's fine, but then you have to go back to your desk and figure out, what thing Mother Nature was using to do her magic. You can't just go in there and say, oh, I observed, I saw with my eyes. Now, as you can see, the rope is intangible. Let me prove it to you. Again, I like to prove this to you, okay, so that I can convince you and make sure you are convinced and educated and finally know. A spoon, you let it go of it, falls to the floor, and something is attracting it downwards. Some people say it's pushing, I say it's pulling. But either way, we can find out that there's nothing that you can touch or see here, nothing that you can touch or see there. And if you're saying nothing came in contact with a spoon, then you're doing black magic, okay? Because you're saying Mother Nature is not, she's a bitch, but she's also a witch. No way. She could be a bitch, but not a witch, okay? Okay, so this fellow continues. He says, we differ in our definition of science. Absolutely. Yeah, I don't know what science he studied, maybe at the monastery. Makes no sense, whatever he comes up with, and we'll see some examples today. I hope to cultivate in emergent scientists a spirit of fearless inquiry, coupled with a commitment to hypotheses that can be what? Tested and falsified. I was going to say reified. Tested and falsified. He's saying that science is about testing and falsifying. Okay, so we're going to falsify everything here? I mean, what is he talking about? You're going to falsify, right? Okay, think beyond the orthodox. Challenge authority, just like he did. He believes everything from authority. He's telling you to challenge authority. But hold to the standards of what? Testability and falsifiability. Well, falsifiability was created by Karl Popper, and he came up with this notion that science is falsifiability. Falsifying, that you're going to falsify or try to falsify something. And a lot of people have the same notion that skepticism has something to do with science. No, skepticism, verification, falsification all have to do with religion, only with religion. They have to do with belief, with what you believe. You falsified God, the other guy says you didn't. The other guy continues to believe in God, so who's right? I mean, again, science has nothing to do with skepticism or belief. That's again part of religion, not science. And so, yeah, he thinks that those are the two criteria: testability. And as far as testing, we have a problem there as well, because, like I just said, you throw the pencil and what test are you going to run? They've been running tests on gravity for since day one. Here's the experiment, okay? There it is, testing. Let me test it again to verify, right? Okay, so what caused that to fall down? I mean, we can't see it, we can't touch it. And so whatever you propose had better be invisible and intangible. Otherwise, you're not imitating what Mother Nature has out there. If you come from the lab back and say, I observed the mediator of gravity, we know you're lying. We know you're lying. You can't observe the invisible. You can't touch the untouchable. And so, as far as Mother Nature is concerned, we're all blind and quadriplegic. We can't see or touch anything in the lab that serves as a mediator for all these phenomena. And so that's where the problem is. Unless you come to grips with that whatever's there is invisible and intangible, you won't resolve it by going to the lab, testing, running an experiment. You got to go to your office, okay? Close your eyes, one beer, a little girl, 20-year-old girl, right? Beautiful girl for inspiration. And you visualize. You try to imagine what Mother Nature could be using. That's the way it works. Okay, so here, one issue that we were trying to address the other day, and he's got the answer to it. That's so great, that we have all these great thinkers out there. It says light bends because you have light going into a prism, and then it kind of bends sharply. It doesn't bend like a curve, it bends sharply like it was broken, and then it breaks again when it's coming out into all those colors, right? And he says light bends because frequency is conserved. And phase must match at the interface. At speed change, rotate at the interface, a speed change rotates the wave vector. Well, even if all the nonsense he just said is true, he hasn't explained it. That's a description. It's called a description. It's not an explanation. He hasn't explained anything. But he doesn't understand the difference between an explanation and a description. And he takes descriptions for explanation and says, oh, I've explained it. And he's not the only, establishment guru, right, or lover that does this. All of them are, they have no idea what the difference is between a description and an explanation. He hasn't explained the cause, the mechanism. He has not explained it. Then he continues, says, N lambda is higher in the blue, so blue deviates more. That's not an explanation. That's a description. It's called a description. The physical cause, okay, now we get to the physical cause of the bend is phase continuity at the boundary combined with a change in wave speed. That's not a physical cause. That's not an explanation. That is a description, okay? And again, that's where the problem is. If you don't know the difference between an explanation and description, we can ask you all day. You're just going to think that you answered the question when you never did. And again, it shows how irrational people think, or if you can call it thinking, right? How they reason or try to reason in their tiny little minds. They first have to find out what the difference is between a description and an explanation. Otherwise, they're going to go around in circles until it take you with them in that circle. So don't try to argue one of these people. They should be locked up in institutions, right? Okay, so here we have, the famous mathematical language, right? Says the physical mechanism behind material dispersion comes from how bound charges in a material are driven by the light's electric field. Well, how can you bind? How can you use the word bound? Bind, we just discussed that a little bit, right? Unbounded, right? How can you bind something, which is a word of physics, when you're talking about concepts such as charges? What is a charge? 1.6 times 10 to the minus 19 coulombs. It's a number. That's what a charge is. They say a charge. No, that's ordinary speech. You can't use the word charge as a noun in physics, not formally. Okay, and then same with field. Field. What is field? Value at each location in space. So you're talking about numbers. And he's talking about binding charges to fields or who knows what. They're binding love with intelligence. Say, oh, love is bound to intelligence. Well, that's great for poetry, but don't bring it into physics. What are you talking about? In physics, this has no meaning whatsoever. Inertia and forces make their response frequency dependent. And again, those are descriptions. They have nothing to do with explanations. Physics is explanation, not description. And these people confuse the mathematical descriptions and they bring them into physics constantly. And they say, oh, we did mathematical physics, right? And that's when they come up with all these mathematical notions which they introduce into physics, casually, like indiscriminately, right? Okay, so here we have another issue there, and as far as math is concerned, here you have a situation. You ask a mathematician. I've had this in the past. You ask them, "What is this? This is a rock, right?" You say, "This is a rock, right?" And they say, "No, that's a mass." "Oh, this is a mass? I thought it was a rock." And no, for them, they don't talk about rock because that's too simple. That's too baby, too kindergartenish. So that's a mass, right? And they start talking about the kilograms and whatever. And you say, "This is a ball," and they say, "No, that's not a ball, Bill. It's 4 pi r cubed divided by 3." "Oh, I thought it was a ball." No, it's 4 pi r cubed, right? Divided by 3. They're talking in terms of volume, of mass, of lengths, and you're trying to ask about qualitative stuff. How does this universe work? I mean, why doesn't the Earth fly out of the solar system? You're talking about a physical object. Hopefully the Earth is taken to be a physical object, right? A big physical object because we're standing on it. It doesn't fly out of the solar system. They say there's nothing physical that they can see or touch between the Earth and the sun. The astronauts have gone around there, and they said we don't see anything, nothing binding it, as they're using the term there, binding. So if it's not bound, why doesn't it, go out of the solar system? Why doesn't the electron fly out of the atom if it's not bound, physically bound? What's keeping the electron there tied to the nucleus? And they never answer those questions. They talk about action at a distance and mediate that distance, that separation, with field, with energy, with force, and other abstract mathematical concepts that have nothing to do with physics. We want to know what physical object is in there, keeping the electron from flying away, the Earth from flying away, the moon from flying away, and so on. And the big problem that mathematical physics has is they cannot explain pull, the force of pull. It doesn't exist in all of mathematical physics, never has. What they have is push. You have lots of push everywhere because they do everything with particles or waves, one-way particles. That means it can only press against something. How do you press at the same time that you pull? Well, the only way to produce pull is to put a mediator between the two objects. See how simple it was? And the only issue there is you got to make it intangible and invisible. And that's where everybody failed, because they could not imagine that there are invisible, intangible objects mediating between atoms. That's where the problem was. They never thought that was possible. Okay, nobody even considered it as a possibility to propose it, at least as a suggestion, let alone for people to believe it. Nobody proposed it. Okay, so here we have this fellow, and he continues. He says, "Bill, what's going on physically?" He's going to try to explain physically what's going on there. "Light polarizes the medium." It polarizes the medium. Yeah, we know that. I mean, why? And he says the field displaces electron clouds. Field displaces something? Numbers? What was the field? Bunch of numbers, right? Value at each point in space. Did I get that right? Or am I missing something? And he says displaces electron clouds. Electrons are bound, right? Physical, right? Bound. Electrons can follow the field. And what are we talking about? What's binding them? And how do they follow a field when field is a concept? So they have all this irrational language that they've created, and they want to get their message across. And nobody understands squat about this because it doesn't make sense. It's a irrational language that they've created. Okay, if they want to talk irrationally in mathematics, no problem. You can keep it in mathematics and talk whatever you want over there. But don't bring it into physics and tell me that you've given me an explanation, that you explain the mechanism, the cause of the physical interpretations. No way. So none of this qualifies for physics. And so, what can I tell you? We have a problem with all these people because they brought this irrational language. They publish using this language, and people say, well, I don't want to read all that technical language. Okay, so we have all these people who serve as mediator and say, oh, we're going to translate what the mathematician said out there in his published paper, and we're going to make it available in kindergarten language for the public. And it's all poppycock anyways. First of all, it's all description. Whenever it's an explanation, it's irrational. Using the same words, field, energy, force, and so on, time. So they have all these irrational terms which they use to convey their theories to the public, and the public doesn't understand squat. And maybe that explains why people have finally forgotten about physics. They say, I don't care about all that nonsense. Yeah, because people have just been bored to death from all the nonsense they hear from the establishment. Okay, so here we have another situation. He says, Fizeau and Foucault measured light in slower in water than in air. Okay, so we know that, yeah. Supporting wave theory and contradicting Newton's corpuscular prediction. Okay, so great. So these guys were in the 19th century. Remember, Newton was in the 17th century, part of the 18th century. And so these guys are more advanced, and they proved Newton wrong, according to the mathematician. There it is. That's official, right? So Newton's particle died. We're done, right? No more particles. And so they said, he continued, double slit, thin films interference, and precise fringe visibilities are predicted by wave optics. Okay, so he's saying it's a wave. We're done. Light is a wave. Over and done with. But then he says, he contradicts himself, single photon. What is a single photon? It's a particle, known as a particle, right? Phenomena and quantizations. And again, quantity, they're talking about quantity, a lump of a value of a unit, a number with a unit. That's what a quantization is. They're talking about numbers, right? It says photoelectric effect, Compton scattering, anti-bunching, etc., all require quantized light, meaning single photon, meaning ball, little ball. And so, he's got a contradiction right there. On the one hand, he says, we've already proven that the particle is wrong, it's wave. And then he says, oh, by the way, some experiments show that it's a particle and not a wave. So what should we conclude? Is it a particle or is it a wave? Here we are, 400 years later, we still don't know. Not from the establishment, at least, right? So, yeah, we have a problem with all their language and what they claim to have proven. He talks about verification. Okay, what have we verified? It's a wave packet. It's a packet. It's a wave. What is it? Particle, corpuscle. What is it? A number? What is light? What mediates light? That's what we want to know. And then some people out there say it's a waving of nothing. So it's a wave, but of nothing. So the nothing waves. And that's what these people believe in. This is how they talk. It's just irrational chatter over there at the math club. Okay, so he says atomic force microscope imaging of molecular orbitals map onto quantum orbital shapes, probabilities. Absolutely not. No, probabilities we don't care about. Shapes we're interested in. But orbitals have shape. Those round balls that you see there, you don't see a little electron bead moving around. Okay, that's what I'm saying here. That's not that atom that you see there is not what you see inside the pictures of atomic force microscope or scanning electron microscopes or whatever. And so we have a problem because these people are saying, oh, we mapped it. Yeah, you didn't map the little electron bead going around. And I'm showing you just the hydrogen atom. We should be seeing little balls running all around there, right? That's what we should be seeing when we look through the microscope, right? Or these advanced microscopes. And that's not what we see. What we see is balls, right? That's what we see. And talks about, binding again. Stable nuclei are composed of protons and neutrons bound by force. Now, you can't bind by force. Okay, again, I put a prisoner there bound to the ball, not with a ball and chain, but by ball and force. Is that about right for physics? You're going to bind your leg to a ball with force, with energy, with field, time maybe, I don't know. I mean, you can't use concepts to talk about binding. You're going to talk about bound, I mean, you're talking about a physical connection. You can't say it's bound by force. But this is the language these people use. They think they're being rational. They've been so brainwashed by all this language that they can't even get out of it. They don't even understand what they're saying anymore. And it doesn't make any sense because the language that they're using is totally irrational. But they just memorize the words and they just keep using them as if nothing. It never occurred to them to question whether, you can bind by force or vibrate a field or transfer energy or move a mass. It never crossed their mind to question the language. Okay? And so when you criticize the language, they say, oh, you're bringing word wizardry, word salad, and you're doing semantics and metaphysics and who knows what. So yeah, this is the issue. The issue is that they have a problem with language. They have to get their language straight if they want to convey their thoughts to the public, and they can't do it. They can't do it because mathematics is completely incompatible with qualitative notions. You cannot transfer, you cannot translate the mathematical notions such as field and so on and say, look, I'm going to take that same word and use it now to explain the physical cause, the mechanism. No, for mechanisms, you need objects, you need things, and field is not a thing, neither is force, neither is time, neither is energy. None of those are things. Okay, so this is where the problem is. Language has to change, at least as a minimum, right? And here's his last one. He says, what is time? Which is what we talked about last time, right? Last time we talked about time. Okay. You don't need to reify time as a material thing, but they do reify it. I mean, there's an example. Warp time. That's what you're staring at. That's what they did. They said, what is the cause of gravity? And they'll tell you out there, not me, okay? Everybody will tell you out there, anyone who is in mathematical physics, they'll say it's the bending of space-time, right? So we're talking about space and time at the same time. We're saying we're bending both of them. We're bending space, meaning length, width, and height, because that's what that little, those lines, that fishnet represents, and also time. So they're bending time. And then he said, we don't need to reify, but you are reifying when you give your physical interpretation. It's plain. I mean, you can't elude it. And you can't say, well, you're not supposed to take it so literally. What am I supposed to do with that? I'm looking for a physical interpretation of why this spoon falls downwards, and you're telling me it's a bending of time. That's what you're saying. Okay, so let's get that straight. That's the explanation that Einstein gave out there. He said it's the bending of time. Forget about space. Yeah, so we got a problem because they're bending time. And what physical, and he says, what's physical are what? The invariants and the intervals. He thinks that's physical. I'm going to hit you with a baseball bat, that's physical. But I can't hit you with an interval or what? Or invariant. I can't hit you with an interval. Time is coordinate with a metric, whatever that means. No, it's not a coordinate at all. Coordinates are longitude, latitude, and altitude, and time is neither one of those, none of those. Time is simply a number line. That's what it was. That's what it's always been. And people confuse number lines with coordinates and dimensions, primarily those two. Okay, and then just in case, we had a second guy or a third guy there. He came over and he kind of synthesized the establishment. He put it in like 3 lines, and I loved it so much I said this is good as a punchline for what this other fellow just said, the clown, right? Here it is, and listen to him. He says, fields in physics aren't just abstract concepts. What are they? They carry energy and momentum. Whoa, have I heard that before? Right here on this channel, I've heard it before. We can measure, mediate the forces we observe. You observe the forces with your eye, like your 2 eyes or 1 eye, or how many eyes you use to observe forces, and transform consistently under relativity. So they're transforming forces or whatever they're observing them. And then he says the electromagnetic field, we're talking about field, right? And not a football field, not a poppy field. Here we're talking about the electromagnetic field, okay? Let's not confuse those. Is so real, whatever real means, right? Exists, that it exists, I guess. That its excitations, photons, right, are the particles of light. So they have these particles, these corpuscles of light, okay? They're going to do light with these corpuscles. And they're saying they're excited. I guess they move up and down as they move forward. I guess that's what they're saying. And so they have these excitations of photons, particles, little discrete packets of energy, which is a number, right? And he says that's the mediator of light. Well, you can't explain light with those particles, because when you do like the slit experiment, you have to put them at two places at once. And they say, yeah, they're at two places at once. And they just get away with that, and it's like if nothing happened. You know, the earth did not shake. So we have a problem because they're giving us an irrational interpretation, walking away like saying, hey, I explained it. Ha, you know. That's why the standard model, based on fields, makes predictions. Oh, the word predictions. That's the language they have. Energy, predictions, verification, falsification. They use all these words. They've just been so deeply brainwashed by all this garbage language, right? Makes predictions confirmed. And what are they going to tell you about the accuracy, the precision of how much they measured and so on? So you measure the table, right? It measures 2 meters and 1 micrometer because you measured it perfectly, right? And then you have it verified by someone else. Obviously, if you want it to be scientific, it's got to be measured by someone else. And the guy measures, he's got a better caliper, etc. And they say, hey, he's right. It's 2 meters and 1 micron. And so you say, okay, give me my Nobel. I measured the table. I mean, is he a scientist because he measured the table? These people say that, oh, I measured it very accurately. Who cares? You haven't explained anything. I still don't understand how the universe works, how the micro world or the macro world works because of your measurement. So they think it's an issue of accuracy, of precision. It's got nothing to do with science. And then replacing all of this with threads, criticizing my theory, right? It's like throwing out the most successful science humanity has ever achieved. Successful? You mean like belief? Is that what he's talking about? See, all these people, they have all this language. They say, we are successful. No, you're not. You still can't tell me what gravity is. You cannot tell me what light is. You cannot tell me how the atom works. You cannot tell me, how magnetism works or electricity. You can't tell me anything. With all your language, with all your measurement, with all your verification and falsification and whatever, you cannot tell me how this universe works. You know, we need to, and, one of the things you have to keep in mind, you have to do it what they call the classical way. You absolutely need to go back to classical physics if you want someone to understand you. If you're going to introduce quantum mechanics, meaning, magical mechanics, where you give properties to your particles that are not classical, meaning they're irrational, meaning they have to do with witchcraft and black magic, yeah, I mean, you can get away with murder as far as an explanation for the mechanism, for the causes. Because if you're going to introduce magic in there and say the particle can be at two places at once, or this particle can affect that one, entanglement without a mediator, you're doing black magic. And so you cannot explain it that way. You have to explain it for people to understand the mechanism. You absolutely need to go back to the 17th century, 18th century, 19th century. You have to go back to classical mechanics, because classical mechanics was attempting at least to try to explain these things in a way that we could all understand it with, mechanism, meaning with mediators and so on. And what quantum mechanics did, and relativity did, string theory also, is eliminate the mediator and say, we don't worry about that anymore. We're never going to figure it out. That's philosophy anyways. It's ontology, metaphysics, word salad, whatever they call it. And we're just going to do measurement and verification and falsification. And that's what we have today. We have a lot of falsification and no understanding. Okay, I'm going to try to answer this other fellow. I gave him a couple rain checks. Gave him one for the bending of light through a prism. And then he asked another question the other day, and it takes a little more time to answer the type of questions he's asking. But hopefully, a lot of people ask these types of questions because they help us all understand. And I'm willing to go out on the line and do a little more research to try to answer these questions. But when these people come up with, like this fellow who said, that talks about fields and energy and all that stuff, he's out of his mind completely. Or he's a clown. He's just, he's funny. He's funny. If he's for real, he's funny. It's funnier if he actually believes in all that stuff. Okay, so this is the question that this fellow asked. Okay, he said, when I rub my hair into a balloon, why does my hair stand up? Well, lucky you, some people don't have hair. But that's the wrong answer. Okay, yeah. Standard science says it's the electrons being knocked off from the balloon. Yeah. So without ions, how does that work? So yeah, if you rub a balloon or you rub maybe a comb or whatever, and you can pick up some little piece of paper, some confetti, right? Okay, so you can do the experiment at home. It's also done by countless people on the internet, right? So you can just look it up, YouTube, and find out that if you just rub something like that's made out of plastic, you can pick up things. There's what they call static electricity. And what we're going to argue today is that it's got nothing to do with static electricity, especially what this fellow said there, representing the establishment, that it's the donation of electrons to the other side, and now you have a negative pole here and a positive over here, and that creates the attraction. Yeah? By what mechanism? Negative attracts positive, North Pole attracts South Pole. What is it? What's the mechanism? That's what we want to know. We want to understand the mechanism. We're mechanics. We're really mechanics. Scientific mechanics. Physics mechanics. Okay, so I have to begin. I'm going to go slowly on this because it's a loaded question, whether he knows it or not. Okay, so let's go slowly. Here's our hydrogen atom, the one we propose. Okay, and it looks like that monster there. Okay, so what do we have there? We have all the ropes from every atom in the universe converging upon our atom. And by the way, that's a picture created by a fellow by the name of Dan. I'm not going to give his last name. I have no authority to do so. I had another fellow named Dave. He gave us the 2D version. This is the 3D version. And I really thank him, and has helped me a lot to be able to convey the theory. So thank you, Dan. You know who you are. So this is our atom. Okay, it's a 3D version of our atom. That's what it looks like. One thread goes through the center of the atom and creates that star-like, urchin-like entity there. And it's encapsulated by what we call the electron shell, or an electron membrane, or electron balloon. Any of those is just fine. Okay? So that's our atom. And that's the one we're going to be working with. Do you believe in that atom? We don't care. We're here to explain to you the model. You take it with you, sleep on it, reach your own conclusions. Here we only present, what we're proposing. Okay, so that's our atom. So far so good. That's so easy. We're done, right? Not so fast. We have a problem there. Okay, and here let me tell you what the problem is. Let's go to the next atom, and that's helium, right? And like on the periodic table, you go from hydrogen. The next one is helium. It takes 4 hydrogen atoms, right? Because you have to compress them inside the sun, naturally, right? To make a helium atom, because it's got 2 neutrons and 2 protons aside from 2 electrons, right? And so here we have it. We're going to try to make a helium atom with all this, and I put a little proton star in there. Okay, you can see that tiny light blue point there. Okay, I put it in there just like that. Don't worry about the actual thing out there. What I'm trying to show here, that it's got 2 protons. Remember, the proton is that part in the center where all the threads, not ropes, threads crisscross. The ropes are always outside the atom. Inside the atom, you only have threads. Okay, so you have the threads going through there, right? And we have another star in there, and we'll call it 2 protons. But we're missing something. What are we missing? Well, we're missing 2 neutrons, right? And so what is a neutron? Well, neutron is a cross point of ropes, not of threads, but of ropes. Not of threads, but of ropes. And people sometimes don't understand the difference. They talk about ropes when they mean threads, and they talk about threads when they mean ropes. So keep those two separate. Ropes are not threads, threads are not ropes, okay? It takes 2 threads to make a rope. They have to be twined, then you can see a rope. Okay, so a cross point of ropes out there in the universe is what we call a neutron. And so we're going to put them in there. So we have 2 protons, right? The one in the center that was there, the other proton that we put in there, and 2 neutrons. Okay, so that's what we have in there. But we're still not done because so far we only have 1 shell. So where's the other electron shell? I mean, it's got to be a shell, right? Or you would think so at least. So we're still missing something here. Okay, we're still missing something. And let's find out if we can modify this so that we can incorporate the electron, the second electron in there. Electron membrane, right? The ball that encapsulates it. So we're going to conceptualize it like this. You can see now it's thicker on the outside, right? The shell. And I'm suggesting, my proposal, right, is that there is a separation between the 2 shells. A very tiny separation there, but there is a separation. So I don't think they're touching, the 2 shells are touching. There is a separation, but it was very hard to kind of illustrate that. If I would have separated too much, it would have sounded like what I'm going to show you later on. And so it would have been a little confusing. All I just want to say verbally, right, is that the shells are not touching exactly, right? There's a space between them, okay? So we have 1 shell on top of another shell. Now we have our 2 electrons, okay? Electron shells, right? Electron membranes, electron balloons. And now we can show here the difference between them. You can see the one on the right has the 2 shells, whereas the one on the left only has 1 shell. Okay, so the one on the left is your standard hydrogen atom. The one on the right is the one we're going to use to make the hydrogen atom, right? Okay, so here it is. We're going to put 2 protons in there. Remember, it's a thicker shell because it's 1 shell encapsulating another shell. And we're going to put a second proton in there. We have now 2 protons in there. What are we missing? The neutrons, right? Always those damn neutrons. Okay, so here we're going to put 2 neutrons in there. Okay, we got that? Okay, so we have now our hydrogen atom. Our helium atom. What is it? A double-shelled electron shell, right? Encapsulating 2 proton stars and 2 neutrons, which are cross points of ropes, not of threads, but of ropes. The protons are of threads, the neutrons are of ropes. Okay? That's our model for the helium atom. Okay, okay. I hope people can visualize that, at least what we're proposing. Do you believe in it? Even I don't believe in it. So please don't believe. We're here to understand, not to believe. Okay, and let's move on to lithium now, the next atom. So we have hydrogen, helium. Now we're going to go to lithium, right? And lithium has 3 protons. And the typical isotope is not 3 neutrons, but 4 neutrons, okay? So just keep that in mind. Okay, so here now you can see how they're, one is encapsulated within the other. But here we're talking about something different. There's a bigger separation between the 1s orbital, which is the one on the inside, and the 1s on the inside, the 2s on the outside, S2, right? The S2 on the outside. The one on the inside, you can see, is thicker, right? Because it's got 2 electrons in there, right? The one on the outside only has 1 shell, okay, so far. Okay, so I just want you to see what we're doing here. We have 2 shells on the other side, one nested inside the other one. There's a tiny separation between them, but both of those are widely separated from the one that encapsulates both of them. Okay, that's what I'm trying to show there. Okay, that's our proposal. Do you believe in it? I don't know if you do or not. I don't believe in it, so why should you, right? And here we put 2 protons. We start there. Okay, so now we have our protons in there. Okay, two protons. Two more protons. In other words, we have the original one and two more in there. Let's not worry right now on how that really is inside there. Let's just put them in there by force. We have to have three protons in there. There you have three protons. The main one in the center and two others, right? What are we missing? Our good old neutrons. There's four of them for the most popular, the most common isotope of lithium. Okay, so let's keep that in mind. Okay, there we have our four neutrons, okay, next to the protons. That's our proposal, okay? And so that's our lithium, but you can see how this is getting complicated. We're at element number 3. Just take it to element 92. You got to go through all these, what is it, the 2s or S2. You got to go through the D, the F, the G orbitals, P also, right? S, P, D, F, G, right? You go through all these orbitals, and it gets quite complicated. They also have different shapes, and you have to think of them as balloons. You've seen the clowns when they work with balloons out there and they make all different shapes. That's what the atomic world is like. It's just a bunch of balloons of different shapes, and they have to take those shapes. The bigger they are, the P, the D, the F, the G. Why? Because they don't fit. A certain spot is taken by the P, so the D cannot use that same spot, so it takes another spot, and then when comes the F, it's got to take another spot. Just trying to tie balloons together, and you'll find out that you cannot have a full circular, spherical balloon. It's going to have all these different shapes because one balloon interferes in the spot where another one is coming in. And so that's why they line up that way, and that's, I think, explains a lot of what we have in chemistry, where we have all these balloons in different shapes, with all these different levels. That's what we're trying to show here. We think it's balloon physics. That's what we'll call this chemistry, these different configurations of the atoms. Okay, so now let's get closer to the question this fellow asked. Let's start working on that a little bit. I showed the other day the covalent bond, and here I'm going to show it only as an s orbital with a p orbital. Okay, this is arbitrary. We just want to show the mechanism. What is the mechanism? Why do we have a covalent bond? Well, you have the s orbital moving in the same direction as the p orbital, and as one comes down, the other one comes up, and that's why they're attached to each other, and we have a strong, what is called covalent bond. Okay? And again, just an example here, we could have two S there's, we could have two P's, whatever, but here we put an S with a P. Okay? That's just an example. Okay, so that's the covalent bond according to the rope model. Okay? That's what we're proposing. You're welcome to criticize it, etc., etc. Okay, now here, we're going to show the ionic bond. But what is the ionic bond? We're saying that somehow, right, because you stimulated an atom, suddenly one thread comes out. And I really think it's more than one thread. I think it's a bunch of threads. But the threads come out, and they're spinning around the atom. Okay? So let me show you first that the thread comes out. Looks like that. I just put one thread. You can imagine this being many threads. Okay, so here, let me show you this. Okay, so it could be many threads coming out. Okay, so either one of those. Okay, again, these are just proposals. This is what we think is happening in there. Okay. Okay, so what happens? How do you create an ionic bond, not a covalent bond? Covalent bond was shell with shell, meshed with shell, and the threads are moving in the same direction for them to be attached, for them to have attraction. And only if they go in opposite direction do they push each other away, but then another atom gets them over there where they go in the same direction. Remember, you have billions of atoms in a tiny, tiny, small space. You have all these atoms going in every direction. When they catch someone that's going in the same direction, they get attached, and that's it. Okay, that's the model we're proposing for chemistry bonding. Okay, bonding, real bonding, like physical bonding, not with words, with fields and energy and whatever nonsense. Okay, so here we have our proposal. What the basic notion here, and I'm going to see it is a simple rotation of an atom. That's what we're saying is happening. What happens when two of these meet? Well, it looks more like that. And you can see as one comes down, the other one's coming up. Why? Because they're both moving in the same direction. That's what we're trying to show here. Okay, so that's where the attachment between two atoms occurs, because in an ionic bond. Why? Because it's not a strong bond as the shell, because the shell is merged with the other shell. Here we only have the threads that have come out loose because you stimulated them somehow. So this is what we call ionization. Okay, ionization and attachment in what we call an ionic bond. Okay, hopefully the images give you an idea what we're proposing here. Okay, we're just trying to get you to understand. And again, we distinguish that from the covalent bond, which is that one. Okay, so that is our covalent bond, shell with shell. The other one is just a few threads. That's my proposal. I don't know if it's one thread. I think it's many threads. They're coming out because you stimulated that atom, and so they're spinning at great speeds. One is coming down, the other one's coming up. So they attach to each other in an ionic bond, which means they're loosely attached to each other compared to a covalent bond, which involves the entire shell. Okay, that's our proposal. Okay, so now, once again, let's get back to the question this fellow answered. I'm sorry I got to give this introduction because I need to take you step by step to the question he asked, which is the why does he comb his hair and pick up papers with it, right? That's the question we're trying to answer. Okay, so here's the official version of that. We're going to have a coat, and we're going to rub a balloon against the coat, and we're going to create what they call static electricity. Okay? What is static electricity? Static electricity says that one of the objects picks up or erases, you could say, any way you want to look at it, picks up all the electron charges from the other guy, meaning leaves them with a positive charge, whatever that is, right? Bunch of numbers. And because one is negatively charged, the other one is positively charged, then one attracts the other. By what mechanism? By magic. It's called magic, black magic. Okay, it's action at a distance. We don't know how it is. We put the word field in there and get away with it, and nobody asks questions. That's the way it's done. Okay, so here we have it. Okay, we have a coat. We're going to rub the balloon against it. Okay, they have charges, whatever those are. It picks up all the electron charges. The balloon picks up all the electron charges, leaves it positively charged, the coat, and you see the negative charges on the balloon, and that's why the coat later on attracts the balloon. Okay, let's see it one more time here. Okay, we have a balloon and a coat. They both have normal charges, positive and negatives, right? We're going to rub the balloon. By doing so, it kind of picks up all the electron charges from the coat, takes it with it, becomes negatively charged, okay? And that's the reason it's attracted, by magic. It's attracted because it's got a potential, it's got a whatever they want to call it, right? And this is a problem. This is a problem because we have no mechanism. They just say, look, one object took the electron charges from the other. Electrons, right? They took all the electrons. Those are negative. I don't know why they're negative. They're like women, maybe men are positive, women are negative. Is that what it is? That's because we men were in charge of physics before the women were. I don't know. But maybe it's female, male. I don't know. The question is that you have all these negative charges, right? And it's negatively charged. It's attracted to the positive charge. By what mechanism? We'll never figure it out. It's just math. Okay? It is so. We have the equation to prove it. Okay? That's all they have. And so here we have the problem with that. One of the problems with that is that the electron is a bead. Okay, so here it is. This is, I think, from the Wikipedia, and it says the following. Give me a second here. So electrons do not orbit a nucleus in the manner of a planet orbiting a star. But instead exist as standing waves. So the electron is not a little particle, it's a wave, right? And I guess they don't understand the difference between a ball and a wave. And there you see a standing wave on the right-hand side and a ball on the left-hand side. How come they can't tell the difference? I mean, you would think this is baby stuff that should have been covered in kindergarten. And yeah, they have these mishmash. You know, they have a language there that does not clarify, you know, what the electron is. Is it a wave or is it a particle? Is it a discrete little ball or not? And you'll never figure it out. And so the problem there says they do not orbit and instead exist as standing waves. No, exist is wrongfully used. Exist requires location, and location is a static concept. You see it at the bottom there in the Universal movie. All the static concepts are concentrated in a single frame of the film. So that's God's film there of the entire universe. One frame contains location only. Location, static concept. What do we have? Distance from one atom to all other atoms in the universe. In a single frame, which you see on the right-hand side there, that's everything had better be standing still. So you cannot say that they exist as standing waves. No, they can't, because a standing wave is something in motion, whereas whatever an electron is, it better be static. You should be able to take a snapshot of it with God's camera, meaning nothing moves, right? And so the electrons are never in a single point location. They had better be. They had better be in a single point at some point in time when you take the snapshot. When God takes his snapshot, he cannot say, oh, but it's moving within my single frame. It can't. There's a problem there. And again, the problem with mathematical physics is it's a dynamic discipline, language, right? And so everything has to be in motion in mathematics. Otherwise, you know, the entire mathematical world is dead. So they don't understand static concepts. They have to, an equation represents a dynamic concept. There is no equation that represents something static, even in geometry. Because in geometry, what it is an itinerary. You do not have a cube. What you have an itinerary around the cube, or a perimeter, or the sides, or whatever. You have a trajectory throughout this object, and that's what they put down as the equation. So, like, you know, earlier I talked about the sphere, you know, 4 pi r cubed over 3. Is that a static concept? No, it's a dynamic concept. What you're doing is an itinerary through the sphere, and you came up with 4 pi r cubed over 3. Now you have the equation for your itinerary. You just have to, you know, replace sometimes the variables in there with numbers. Okay, so here we have, that was the wave version. Now here's the particle version, because, you know, they never resolved this. Particle-like properties of the electron, right? Number of electrons orbiting a nucleus can be only an integer. So by that they're saying it's got to be like a little ball, a little point, right? Because we can specify it with a single number, right? So it's got to be an integer. Electrons jump between orbitals like particles. So if they jump between orbitals like particles, is the electron a wave or a particle? How can it be both? Again, you know, they've never resolved this. And this is not an issue of going to the lab, because you're not going to observe, you know, using your eyes. You're not going to be able to touch using your hands. This is something you do in your office. You look up, a girl for inspiration, and you visualize. You try to imagine what Mother Nature could be doing in that secret world of hers. You got to conceptualize. That's a theory. You cannot come up and say, oh, I went to the lab and observed. What are you going to observe? You can't observe an electron. You can't observe light, the mediator of light. You can't observe the mediator of gravity. So observation, tests, using your hands, tangibility, none of that has any bearing on the question we're asking. The question we're asking has to do with theory, with conceptualizing only. And then you have electrons retain particle-like properties. And you go, each wave state has the same electric charge as its electron particle, whatever that is. Because again, they're talking about math, and they say it's got a single charge. What what is it, 1.6 times 10 to the minus 19 coulombs, the value of the unit charge, right? Each wave state has a single discrete, what? Spin. So they spin, but they don't spin, because spin is not spin like a top. It spins, whatever that is. So you have a zero-dimensional or a particle that has no volume, essentially. And they say it spins. Well, I've never seen a zero-dimensional anything spin. But assuming it's got a little size, a minimum size, fine. Okay, does it spin? Now they say we call it spin, but that's only to mislead you, because they don't know what spin is. But then they always illustrate it as spinning like a top. And so again, we have the wave. Does the wave spin like, sideways, or what are they talking about? What's spinning? Is it the ball? I mean, how do they know it spins? Well, it's just a number. Spin is a number. They call it spin to mislead people. They illustrate it as spinning, as a spinning top, but then they, at the end of the presentation, they say, oh, by the way, we weren't talking about spinning. So what were you talking about? You weren't talking about spin. Why did you use the word spin? Oh, because it's tradition, Okay, so here we get down to the orbitals, okay? And that's what you find for the orbitals. You have the S, the P's, the D's, the FG's, and so on. And what you have is, you can see they have different shapes, okay? All these orbitals. And this is what they mapped using Heisenberg's equation, essentially. Schrodinger's equation, okay? So that gives them an idea of what could be in that world of micro world of Mother Nature's. Okay? So these are the orbitals, and we're saying that our model, the rope model, matches this perfectly. Balloons, that's what you're staring at. And those are the different shapes of the balloons. The more balloons you put in there, they have less room to do like a circular one, a spherical one like the S or orbitals, and they have to have these other strange shapes. Okay, and so we're saying this is perfectly for the rope model. Yeah, what we've been looking at all these years in that little tiny world are balloons. Okay, they're not orbitals. Orbital is a concept, so is an energy level. Those are concepts. And they say, well, it's where you can find the electron bead. No, the electron's not a bead, because if it's a bead, you can't do anything with it, because how are you going to explain action at a distance? You're going to have to introduce angels, spirits, or mathematical concepts, which is what they've done. They've introduced, field, time, energy, force, and so on. Okay, so here we have the orbiting bead again, okay, just in case. So when we look at these orbitals, they say it's mediated by an atom like that. And so this clown that was trying to tell us that, orbitals map perfectly well with what we get out of the atomic force microscope. Absolutely not. What we're seeing there is a ball, and what we're seeing here is a little ball that's going around another one. And that's not what you see there. That's not what the atomic force maps. Okay, so let's make sure that's absolutely clear. Okay, so what happens when you rub plastic? Well, you rub plastic, and now you can pick up all these papers, or you comb your hair, and you can pick up paper. There's what they call static electricity. How do we explain it? They explain it by saying they left the electrons, or pulled out the electrons, depending on which of the two objects you're talking about. One becomes negatively charged, the other one positively charged. And now because one is positive, the other one is negative, we all know that positive attracts negative, women attract men, sometimes. And they come together. There's attraction. We have pull, okay? How do they explain pull? We have no explanation. It's just black magic. How do we do it with the rope model? Well, we have these threads going around, as I just explained, ionic bond, right? So if they're both going in the same direction, the threads that are spinning around the atom that has been stimulated and has released some threads, and that these threads are going around, one comes down, the other one comes up, and now you have an attachment. And I'm saying that's what's happening with plastic. When you rub plastic, you're stimulating the atoms. They're twirling around at great speeds, right? Releasing a few maybe one, but I think it's more than one. I think they're releasing a few of the threads, not rows, threads around. They're spinning around the atom, and they're coming up with the atoms of the paper, or perhaps the entire paper. Maybe it's just sweeping the paper up, because remember the strength of a static electricity is not very strong, not like a magnet. A magnet can attract things much more, stronger. You can see it here. I don't think you can do that with static electricity this strong, right? And then the question is, well, if the threads are spinning around, several of them, and you have a magnet, why doesn't a magnet attract the plastic? Okay, because you have, the spinning of the threads in a magnet, and you have the spinning of the threads in a plastic, which is amorphous, right? See, you have this situation. You have, in magnets, you have domains, right? And when you align them, like you see at the bottom, right? All the atoms are pointed in the same direction, or spinning, their threads are spinning in the same direction. So you have all these groups of atoms, including the domains themselves, right? And they're all contributing one to the other to pull. You have gazillions of threads going in the same direction. That's not the situation you have with amorphous materials such as, for example, plastic, right? Could have also with glass happens as well. They're amorphous. And that means that the atoms that form the molecules themselves, they have their threads spinning in all kinds of directions. They don't have domains where you can align them all in the same direction, for otherwise you would have a strong magnetic field. What you have is the threads going in different directions, and that's why it's much weaker than the ones produced by a magnet. And so what's the issue? The issue there is, first, that explains why the magnet does not attract plastic, because it's not, you don't have what another magnet would have, which is going in the same direction, all the threads going in the same direction. Here you have them all going in different directions, but remember the threads extend far out from the plastic, and they are able to catch, the paper on your table. And but you have to be kind of close for them to do that. You can't do it from out here. It's not that strong. And again, it's not that strong because they're not aligned. So you have, all these threads spinning around because you've stimulated the atoms, right? And so now they're spinning around and they're pulling them up. Okay, they're pulling all these atoms up, and they don't interact. The threads from a plastic do not interact with a magnet because, again, they're all going in different directions. And a magnet has no way of attracting something that has all these threads going in different directions. Okay, so the threads are stimulated out of their atoms. They're spinning around, but they're all going in different direction. In a magnet, they're all going in the same direction because the domains are aligned. And I'm going to open up the floor for questions. Anybody want questions? Go ahead. I hope you believed everything I told you today. Fellow says all my charges are negative. My credit card is too negative. No, it's called. It's not negative. It's called. What is it? Irrational time. Well, here you have irrational money. The other direction. Yeah, all these crazy guys, so-called philosophers and whatever. It's just unbelievable what a mess they've made of science. That's what's so heartbreaking about it. And we've been at this for at least 2,500 years, the days of Plato and so on. But if you go farther back, even to the Assyrians, Sumerians, they probably asked these questions as well. How come my pencil falls to the floor, etc.? And here we are, maybe 3,000, 4,000 years. No one in mathematics can answer that question. Simple question. It's a baby question. It's a question of kindergarten. And you're saying, well, it's not so easy. It is. It is. All you had to figure out is what comes in contact with spoon. That's the rational part. But if you can't see it or touch it, that doesn't mean that there's nothing there. And there you have to go to the definition of what an object is. An object is that which you can, that has shape, not that you can see or touch. And they were always looking for see, touch. They say, well, I can't see anything, I can't touch anything, so there's nothing there. Wrong conclusion. And we still have that in formal physics, formal science out there today. Okay, let's see. We have one question. Has physics and science ever updated, changed example, spin, change example, spin and balls model? No, really, we've been with the stick and ball, because they, like in chemistry, they have the stick and ball model, right? They've been using balls for the last 4,000, 5,000 years. Everybody thought in terms of particles. In fact, the wave came up in 17th century, and that was with our good friend Robert Hooke, who was looking through the microscope, and he was seeing kind of wavy things. He said, hey, you know, maybe light is a wave, the waving of the ether, he thought, right? And that's when they got in a debate between the wave theorists, people like Huygens and people like Newton. It wasn't resolved until the early 19th century by Newton's own countryman, Thomas Young, who said, hey, Newton, you're wrong. It's a wave. And they have this wave, which lasted throughout the 19th century. And then in the 20th century, they went back to the particle, and now we have the particle wave, but they really got rid of the wave completely. And now they replaced the wave and the particle with fields. Why? Because it's an extended notion, extended concept, and they say, hey, we better use the field because that can help us unite quantum mechanics with relativity. And that's what they're working on today, all the equations for that nonsense. Okay, here. Okay. Recent research video that showed an experiment of how a balloon wasn't attracted to the hair, namely, I proved static electricity makes no sense. Can you review that video? Okay, I'll take note of that. The guy proves what? That static electricity makes no sense. There is no such thing as, let me clarify that, maybe that wasn't clear. Static electricity just means, why do they call it static? Because there's no current running through there. They just say what's happening is we donated the electrons to the other side, and now the other side is negative and we're positive. And because they're negative and we're positive, we're attracted to each other electrostatically. Right? So now they're talking about electrostatic because they said this has all to do with electricity, but not the conventional electricity, which is the flow of beads. Here they're saying the beads are not flowing, they're just on the other side. It's more negative over there, and that's why there's an attraction. But again, they cannot explain how negative attracts positive, which is what we want to understand. If we don't understand how negative attracts positive, they could have said X attracts Y. Women attract men, you know, I mean, they could have said anything. I mean, you know, we need a mechanism, and we don't have that mechanism today. What is sound or vibration based on the ropes? It's not based on the ropes. Sound is an issue of atoms, okay? It's not an issue of ropes. It's got to do with the atoms themselves. They're vibrating. That's what's hitting you in your ear. You have molecules, really, but atoms form the molecules. They're vibrating in the air. That's why you can hear me. And they're pounding against your eardrum, which, through evolution, we gotten used to listening to sound. In fact, they say one of the first critters to have hearing was cacops. So if you look up cacops, you'll find that he's the first guy that they found that's got an eardrum. Anyways, yeah, it's atoms. Atoms hitting your ear. That's why you can't hear in space. Even though there's ropes crisscrossing the entire universe, you can't hear in space. Why? Because there are no atoms to convey the sound. There's no sea of atoms. There are atoms out there, but not a sea of atoms, billions and billions like we have here on Earth that are, you know, making your ears vibrate. Okay, see, the guy in the video showed that if you rotate the balloons to the side, it attracts the hair, but if you rotate the balloon, obviously it doesn't. Yeah, I was looking at that because one of the things they say, which is the one that I was looking into, was that if you rub like with a cloth, wool, right? You rub a plastic, right? Well, the plastic will attract a piece of paper. Does the wool that is now positive, does that attract a piece of paper? And they say, yes, it does, but it attracts the paper on the other side of the paper, on the positive side of the paper. That's got to be understood a lot better, because if the wool also is attracting that, that means the wool has also the atoms of the wool, according to the rope model, right, are also spinning their threads around, but in the opposite direction. Positive, negative is clockwise versus counterclockwise. That's all it is, really. That's what Mother Nature understands. So the atoms that comprise the wool are spinning their electrons in the opposite direction. In that sense, you can say, yeah, this guy became positive, this one negative. Why? Because by rubbing them, one went this way and the other one went, and the other, let's get them right. One went this way and the other one went that way. So they're both going in opposite directions. Okay? So now you have a piece of paper in between, and there's a tug of war. The one guy, the negative side wants to take it that way, and the positive side wants to take it that way. Right? That's what they're saying. That one side of the paper is attracted to the positive, the other side is attracted to the negative. And that's one possibility. Let me give you another possibility, which I just kind of glossed over, but just so you understand. It could be that the threads are picking up the whole paper. The paper's not charged at all, perhaps. I mean, this is another possibility. And since the threads are sweeping around, the paper's so light, right? And again, you're talking about threads that are going in different directions, but they extend far out. So they're picking up the paper somehow. It's another possibility. I still believe that the paper somehow has been charged, because you would think that the paper at a very low level has also some threads that are moving around. Okay, so these are things that, unfortunately, we don't have the eyes of God to see in there, so we have to try to imagine what could be happening there. Okay. What makes the rope to form the atom? It's not that the rope, that there was a God that said, okay, I'm going to convert all these ropes into atoms and blah, blah, blah. No. The universe has always been there. All atoms in the universe have always been interconnected. How many atoms are there in the universe? A lot. That's a very accurate number, okay? It's gazillions. Another accurate, very precise number. There's gazillions of atoms in the universe. If we were to unravel, this is just conceptually, right? If we were to unravel every atom, every rope in the universe, we would end up with a, if I have one here, I don't, with a single thread. Very thin, enormously big thread. That's if we were to unravel them. So if you started at one atom, you went through every atom and every rope in the universe, you would come back to your starting point, because it's a closed loop thread. Okay? But it's not like someone built it and said, somehow it got formed. It's an emergent property. No, the atoms and the ropes have always been there. No one created them. And space cannot turn into atoms, and atoms cannot turn into space. Atoms cannot leave space, because space does not have a border for you to cross. Not even God can escape space. So what we have is that the atoms have always been there. No one created them. No one moved a magic wand and said, I'm going to create atoms. They were always there. Okay? The universe is eternal in both directions of time. Okay? Okay, I guess that's it. We'll call it a day, and we'll see you next week. Bye-bye.